This is week 2 of problem solving session for applied thermodynamics course. The course instructors are Niranjan Sahu, Professor Niranjan Sahu and Pranab K. Mondal. So, the previous week we had a brush up of the basics of the thermodynamics, the first law, second law, and so on. So, this week is on the vapor power cycles, or specifically a Rankine power cycle. Before going to that, we will see some what is a Carnot cycle, and then compare it with the Rankine cycle. So, and we will see if we can apply the exergy concepts to some of the problems. So starting with Carnot cycle. So Carnot cycle basically, as shown in the figure, has 4 processes. So starting with, we have an isothermal heat addition, so 1 to 2, where you maintain constant temperature, and then you have 2 to 3 isentropic expansion, so it's a reversible adiabatic process, and then 3 to 4 you have again isothermal heat rejection, and then 4 to 1 and isentropic compression. So these are the 4 processes, so consisting of 2 isothermal and 2 isentropic. So this if you see, it's just another way of showing the turbine using a turbine. So isothermal type turbine, and then isentropic turbine, then you have isothermal compressor, and then isentropic compressor. So if you observe, normally isentropic process or reversible adiabatic. So in actual cases, none of the processes is reversible. So assuming you are close to a reversible process, and so it's an adiabatic. So it's an easier process. You have to just insulate the turbines and to reduce the heat which is going out or coming in. So there is no heat interaction. So that's an easier process. And normally speaking, your compressor or turbine or whatever engines or whatever system you see are running at very high speeds. So for if you say a 50 Hz cycle, so into 60 seconds, so it's close to 3000 RPM rotation in which the shaft rotates. So you have very minimum fraction of seconds. So in that fraction of second, there is hardly any heat transfer, you can say. Very small, less time for it to have a heat transfer. So that is an isentropic process. That's why we assume that most of the expansion and compression processes here are reversible adiabatic, because the process itself is very fast. So the Carnot cycle, this has 2 isentropic processes. One is compression and one is expansion. The other 2 is an isothermal heat addition and isothermal heat rejection. So in an isothermal process, compared to an isentropic has only heat interaction, work interaction, there is no heat interaction. But comparing that with an isothermal process has both. It has both heat interaction as well as work interaction. So, and you need to keep, for it to remain at constant temperature, it has to constantly reject or gain heat. In an expansion process, it has to gain heat, and in a compression process, it has to reject heat. So it has to do both the processes simultaneously. It should have both heat interaction and work interaction. It is difficult to achieve, and this for it to be an isothermal process. Again speaking, I told about an adiabatic process having very fast process. So in an isothermal process, this has to be very slow. So happening at very slow, such that it rejects heat and comes in equilibrium having a constant temperature. Then seeing the cycle, it has 2 processes which are very fast and 2 processes which are very slow. So having this is one of the problem in a Carnot cycle, physically speaking. And also in the other limitations are for having to be in constant temperature process. If you put it in you can then go again and then put it inside of a vapor pressure dome. So there you are converting that into an isothermal to an isobaric process, because for fluid, the phase change occurs at constant temperature. So you can very well say that it is an isothermal process. So, but it's occurring at a constant pressure, so isobaric. So you can convert that by putting it in a two-phase dome. So the top image on the right shows a Carnot cycle inside a two-phase region. So if you see in this case, the problem here is then also in a Carnot cycle, physically speaking, the heat exchange sizes should be has to be very large for it to have a constant temperature. So so there is always be heat transfer, so you need a temperature difference between the cooling medium or the heating medium and your gas inside the cycle. So physically speaking, there should be some temperature difference. But in a Carnot cycle, ideal Carnot cycle, there is no temperature difference between the heat source and the fluid. So that requires you having a heat exchanger of very large, bigger sizes. So if that is what is required, so the process 1 to 2 and 2 phase dome, your heat exchanger size is very large for delta T too small. But physically speaking, for having a large heat exchanger size means you have a large pressure drop. So there is a problem there. So this all are the problems which happens to physically construct a Carnot cycle. And then again the fluids will be in a two-phase region at for states 3 and 4. Even though it's in saturated state at 1 and 2, 3 and 4 is a wet steam, for example, or it's in a mixture of liquid and vapor. So handling this in a turbine or a compressor is very difficult. Having a two-phase in your turbine, so that will have a different velocity, so it impedes the turbine blades and it can damage. So there will be other set of problems which will be arising because of having a two-phase fluid. So these all limits are use of a Carnot cycle in a practical system. And the other disadvantage, if you say, Carnot cycle is independent. It's independent of fluid. So whatever the fluid may be, you will get a maximum efficiency out of a Carnot cycle. But that also comes at a cost. So if you are hypothetically can build a Carnot cycle, so then what happens is the individual component, the processes 1 to 2 or 2 to 3, having a turbine or any component, its initial capital cost will be very high because you will require a very big, as I told, heat exchangers or compressor. So per even though the efficiency is large, but each component requirement is of a huge capacity. So that also limits are used. There's also a limitation because of that. So how do we overcome this? So the other way of overcoming is this. As I told, we can go from an isothermal to an isobaric process. We can convert it to an isobaric process, and again, we have to avoid this wet region or a two-phase flow. So we shift this Carnot cycle at the top, so such that 3 to 4 is in it's a saturated state. So this is one kind of arrangement you can have. The easier way, it's again a gas power cycle. So the other easier practical way of having a cycle is having a Rankine cycle. So what happens in the Rankine cycle is, so we are converting, so we had two isentropic processes that remain same, but this process are happening outside the two-phase zone, and we are converting the isothermal processes into a isobaric processes. So we have two isobaric processes and two reversible isentropic processes. So if you see, 1 to 2 is an isentropic compression. If you see here, this is one is a saturated liquid. So we're compressing liquid to pumping the liquid to state 2, 2s for an ideal case. So this makes a larger sense because the work done on any fluid is minus V dP. So here your specific volume of your liquid is very small compared to any gas. So in that case, your work done as for your pumping or process of compression for a gas is very small for a liquid compared to a gas. So it's make a better sense to have a saturated liquid to be pumped to higher pressure. So you're pumping that on higher pressure, and then you add heat to first convert into from subcooled state to saturated liquid, and then to there's a phase change that happens to saturated vapor, and then you superheat it to some state 3. You can also avoid that by superheating, and you can expand from saturated vapor, but then you'll have a two-phase at the exit of the turbine. So to avoid that, you superheat it to state 3 and then expand such that you reach a saturated vapor at the exit of the turbine. And then again, that's an isobaric heat rejection. So the actual system looks something like this. So we have a pump. So we have a pump which pumps the fluid from state 1 to 2, or in an actual case, and 2 is to an ideal case. And then in a boiler, we add heat and we convert it to a steam. So that steam is then passed through a turbine which expands, and then we condense it in a condenser and then bring it back, and it goes through a cycle. So the equations, this is how the equations look for each of the component. So through each of the component, your mass remains same because it's a closed loop and there is no exchange of mass between any surrounding. So your system mass remains constant. So that's the mass balance you have. Then if you do an energy balance, so for pump it looks like this: m dot 1 h1 plus work in equals m dot 2 h2. So from first law, and then similarly you can do an entropy balance. So m dot 1 s1 is the fluid entropy coming in plus s generator equals m dot 2 s2. Then you can have an also write an exergy balance. So exergy balance is nothing but your combination of your first law and second law. So if you have that equation, first law energy equation and entropy, if you subtract it, multiply by T naught and subtract it, you'll get the exergy balance. So this will come out to be m dot 1 xex1 plus w in equals m dot 2 ex2 plus your exergy destroyed. So this is for pump. Similarly, you can write it for boiler. So boiler m dot 2 h2 plus q in equals m dot 2 h3. So that gives the amount of heat which is given in. And if you do an entropy balance, it is m dot 2 h2 plus q in divided by T source plus S generated in the boiler and m dot 3 s3. So similarly, you can write exergy balance, and the other equations for the other components is given. So now we'll go ahead and see some problems. So the first is the component of the steam power plant in which the working fluid vaporizes is the A. boiler, B. condenser, C. pump, and D. turbine. So the answer is option A, boiler. So as we saw in a Rankine cycle, we have 4 components. So one which is happening converting your liquid to vapor is your boiler, where you add heat and the liquid which is pumped, it comes in a higher pressure, so from subcooled state you convert it to saturated liquid and then saturated vapor and you superheat. So this is what the process occurs in the boiler. So the answer is option A, boiler. The next is, which of the following is not a primary goal of subsystems associated with steam power plant? So A, convert shaft power to electrical power. Option B, convert electrical power to shaft power. C, supply energy to vaporize the power plant working fluid. Option D, provide condenser cooling water. So out of these four, which is not used or is not a primary goal of any of the subsystems? So the answer is option B, convert electrical power to shaft power. So it's a Rankine power cycle, so you are getting work. So you are doing, you have shaft power and you can convert it to an electrical power and send it to a grid. So it's not the other way around. So option B, convert electrical power to shaft power. Even though a small amount of power is used in compressing power, in pumping fluid, it can be electrical, but it can be coupled to a turbine or from the work which you are generating, it can be done. So this is not the major goal. So answer is option B, convert electrical power to shaft power. The next question is, the component of a steam power plant that requires a power input and the component in which the working fluid rejects energy by heat transfer are dash and dash respectively. So which are the component which requires power input and which condenses? So answer is option B, pump and condenser. So pump is the one which requires some power for it to pump or compress the fluid to a higher pressure, and then condenser is where your fluid rejects energy. So you have a vapor, saturated vapor. In an ideal case, you can condense it to a liquid state for it to be pumped. So there you have to do an heat rejection. So that will have some cooling coils and so on, or a cooling tower where you will reduce the you will reject the heat. The answer is option B, pump and condenser. Next is, which of the following component of steam power plant is with the largest exergy destruction? So which of the following component of steam power plant we have maximum exergy destruction? Option A, pump. Option B, condenser. Option C, boiler. And option D, turbine. So the answer is option C, boiler. So the maximum exergy destruction will happen across boiler. So there you will have a source temperature where of a heat source. So you are supplying heat to the boiler, and because of the huge large temperature difference, that will create entropy generation. So that will cause larger exergy destruction. So because that heat source, if you are ideally speaking, you can run an Carnot cycle, so that will give you a maximum use of that heat which is taking from the heat source. So suppose the heat source is at so if we go back to the previous cycle, so option 3, so suppose you have so water, and this is at a higher pressure, so you say something around 200 degrees Celsius, and you're superheating till some 300 or 400 degrees Celsius at 3. So but your heat source is at should be at higher temperature, or else there will be no heat flowing, so you need a temperature difference. So your heat source should be something even higher than the temperature 3. So the temperature comes very close only at state 3, where you have minimum temperature difference. So if you see your temperature difference between the heat source and your state 2s or 2, so there's a very large temperature difference, and it gradually reduces till 3. So this much of the area in a TS diagram is not accounted. So that creates a large exergy destruction. So the answer is option C, boiler. So next is match the following. So you have 4 components of the Rankine cycle and also the 4 processes which is used. So which component goes through which process? So boiler. So boiler is a constant pressure heat addition. So answer is first is B. Then turbine is a reversible adiabatic expansion of steam. So option A. So we say answer is option A here. Then again condenser is constant pressure heat rejection. So option D. And pump is reversible adiabatic compression. So 3 is C. So answer is option A. So moving on, in a vapor power cycle, enthalpy of steam at inlet and outlet of turbine are 2800 kJ per kg and 1800 kJ per kg respectively. If the pump work is neglected, find the specific steam consumption in kg per kilowatt hour. So in a vapor power cycle, your enthalpy of steam at inlet and outlet of turbine is given, which is 2800 kJ per kg and 1800 kJ per kg. And if you neglect pump work, find the specific steam consumption in kg per kilowatt hour. So see how to solve this. So your net work is your turbine work minus pump work. So pump work we are neglecting. So turbine work is m dot into your delta H. So specific steam consumption is nothing but your fluid which is you are taking how much steam is being used or the mass flow rate. So you need it in kilowatt hour. So you multiply by 3600 and divide by 3600. So 3600 divided by, so this is for per kilowatt of per work output, how much steam is being used. So 3600 divided by W net. So W net is enthalpy W net. So 3600 divided by your enthalpy difference 2800 minus 1800. So this will give me 3.6 kg per kilowatt hour. So it requires 3.6 kg of steam flow for per kilowatt hour of work output from the power plant. So the next question is, in a Rankine cycle, consider the work done by turbine during steam expansion is 3500 joule. So in a Rankine cycle, your work done by turbine is 3500 joules. Note that the pump work to feed back the water into boiler is 1300 joules. The work ratio will be. So what is work ratio? So work ratio is nothing but your net work divided by the work you are generating. So how much work you are getting but out and how much you are able to generate. So work you are getting is from the turbine. So the turbine work, and the net work is your work you are generating to the turbine minus the amount of work which is utilized by the pump. So here we know the turbine work is 3500 joules and the pump work is 1300 joules. So 3500 minus 1300 divided by 3500. So this gives you 0.628 or 0.63. So the work ratio will be 0.63. So next is, the Rankine cycle is considered as an ideal cycle for steam power plant owing to the fact that water enters pump at unsaturated state, it produces maximum turbine work, It includes reversible processes. It does not allow isentropic expansion. So this we are saying it is an ideal cycle because we are considering all four processes are reversible processes. So hence we are calling it as an ideal Rankine cycle. So the next question is, consider the following statements regarding the Rankine cycle for steam power plants. So Rankine efficiency of steam power plant is higher in the winter season compared to the summer season. So this high Rankine efficiency in winter season is because of the lower condenser temperature. So there are two statements, so we have to see whether each statement is correct. So they say Rankine efficiency of a steam power plant is higher in the winter season compared to the summer season. So that is one statement. Second statement says that this high Rankine efficiency in winter season is because of your lower condenser temperature. So answer is both 1 and 2 are incorrect. Sorry, so the answer will be option A, both 1 and 2 will be correct because you have a lower condenser temperature. So in that case, you have maximum work done, your net area under the cycle will be larger, so you will have a higher efficiency. So it's a mistake, it will be both 1 and 2 are correct. So which one of the following statement is correct? Work ratio and efficiency of Carnot cycle is higher than the Rankine cycle. So work ratio and efficiency of Carnot cycle is higher than the Rankine cycle. Work ratio and efficiency of Carnot cycle is lower than the Rankine cycle. Both Carnot and Rankine cycle have equal work ratio and efficiencies. Option D, work ratio of Carnot cycle is low and the efficiency is high in comparison to the Rankine cycle. So answer is work ratio of Carnot cycle is low and the efficiency is high in comparison to the Rankine cycle. So this can go back to what discussion we had on Carnot cycle. So where I told each of the component will be a larger size, so the capacity of each component will be larger. So that means your turbine and compressor capacity will be larger. So your net work which you are getting will be small. So if you say 1 kilowatt of work which you are getting from a Carnot cycle and from a Rankine cycle, so your turbine and the compressor work capacity will be even more larger, 3 to 4 times larger, suppose. So like you have 4 kilowatt just I assumed, so this could be we can see some problems, but so you are comparing Carnot and Rankine. So Carnot will have say for turbine 4 kilowatts and compressor 3 kilowatt, but in a Rankine cycle you will have something close to 1.2 kilowatt and your pump work. So if you see the each component capacity is very larger in the Carnot cycle. So your work ratio that is nothing but W net divided by your turbine work. So your turbine work itself is large in Carnot cycle, the capacity. So and then compared to the network, so that will create a smaller uh, work ratio compared to a Rankine cycle, or the other way around. If you see, pump work is very small, the compressor work will be very large. So for a given turbine, your net work generated will be small in a Carnot cycle compared to a Rankine cycle. So in either way, your work ratio will be small for a Carnot cycle, and then efficiency, the highest efficiency any cycle can provide is the Carnot cycle. So Carnot cycle will give you the maximum efficiency. So work ratio of Carnot cycle is low and efficiency is high in comparison to the Rankine cycle is the correct option. So now we'll move on to see some numericals. So we'll see some, first starting with a Carnot cycle example with steam cycle. So heat source temperature is 300 degrees Celsius and heat sink temperature is 20 degrees Celsius. So what is the thermal efficiency and to ratio of turbine work to compressor work if all processes are reversible? Neglect the change in kinetic energy at inlet and outlet of the turbine and pump. So for a reversible cycle, we can straight away find out the thermal efficiency of Carnot cycle as 1 minus Q1 by T2. This is nothing but your W by Q, and W you can write it as Q1 minus Q2, and because the Kelvin temperature scale, you can say Q or from Clausius inequality, Q1 by T1 equals Q2 by T2. So we can express efficiency as 1 minus T1 by T2. So we know the heat source temperature and sink temperature. So source temperature T2 is 300 plus 273, so 573 Kelvin, and T1 is 273 plus 20, 293 Kelvin. So this will come around 0.489 or close to 49%. So now we'll see these are we'll have to find out the ratio of turbine work to the compressor work. So state 2 is in isothermal or isobaric process. So for water or steam, so at vapor at 300 degrees Celsius is enthalpy is 2749 kJ per kg. So this we can get from a steam table, and similarly your entropy is 5.7045 kJ per kg Kelvin. We know that the expansion is occurring at a constant entropy or an isentropic process. So SC will be equal to 5.7045. So at state 1 or 20 degrees Celsius, corresponding to that temperature, your fluid saturated liquid entropy is 8.3706, and your saturated vapor entropy is 0.2966. So using this we can find out your vapor fraction at state C. So that is nothing but your S equal to SF plus X into SF SC minus SF. So rearranging, we can find out the vapor fraction at C. So this will come out to be 0.646, and then again at D we can find out the entropy, which will be equal to entropy at state A, which will be 3.253. So from there we'll find out the vapor fraction at state D is 0.353, and so because D is less than C, because you are condensing vapor, so your amount of vapor at state D will be lower. So which we can see is 0.353 compared to 0.646. So from using this vapor fractions, we can again find out enthalpy at state C and D. So your vapor fraction into your latent heat plus your liquid saturated liquid enthalpy. So that will give me 1669.4 kilojoule per kg at state C. Similarly, at state D, my enthalpy will be 950.8 kilojoule per kg. So we know now enthalpies at each of the states. So my turbine work will be difference in enthalpy HB minus HC, and for compressor will be A minus D. So turbine work is HB minus HC, which is 2749 minus 1669.4. So this gives me 1079.6 kilojoule per kg. So if you have 1 kg per meter kg per second of steam flow rate, then you'll have close to generating 1 kilowatt of work in a turbine. And if you see compression work is your HA minus HD, so that will give me 1344 minus 950.8, which is 393.3 kilojoule per kg. So if you see this is 400 and then 1000, so you're close to generating some 650 kilowatts of net work from the turbine. So if you have a same cycle or in Rankine, so this amount will be a smaller quantity, because your pump work will be very small, so you not require that high compressor. Again, but your efficiency will be smaller compared to this Carnot cycle. So moving to the next question, a heat engine receives 100 kilowatt heat from a source at a temperature of 1000 Kelvin. So you have a heat engine which receives 100 kilowatt heat from a source. It is at a temperature of 1000 Kelvin. The heat engine produces a net power output of 30 kilowatt, and the heat is rejected to an environment with a temperature of 25 degrees Celsius. Write the overall mass, energy, entropy and exergy balance equations. Calculate the amount of heat rejected to the environment. Calculate the amount of exergy destroyed and exergy rejected to the environment. And D, find the energy and exergy efficiencies of a heat engine as well as reversible Carnot efficiency. So what exactly is happening is, we have a heat engine which is receiving 100 kilowatts of heat from heat source temperature of 1000 Kelvin, and it's producing a power output of 30 kilowatts, and it is rejecting heat to a temperature at 25 degrees Celsius. So we'll see how to solve this problem. So the first case is we have a mass balance, so M is constant. So next is your energy balance. So that is if you consider the whole heat engine as a system, so there is heat which is coming in, and you are generating some work, and the rest you are rejecting it to the sink temperature. So Q in equals Q out plus W net. So this gives me the energy balance. Next is an entropy balance. So the entropy generated because of the heat addition is Q in by Th. So assuming it occurs at constant temperature, then S generated equals Q out by the sink temperature. Similarly, you are subtracting the first energy balance equation minus T naught into the entropy balance equation, you will get the exergy balance equation. So exergy because of Q in, exergy because of Q out will be Q in into 1 minus T naught by Th, and Q out will be Q out into 1 minus T naught by TL. T naught is your ambient temperature, and then W net is net which you are getting, and exergy destroyed is minus T naught into S gen. So with this we can find out the first, calculate the amount of heat rejected to the environment. So Q in is 100 kilowatt, Q out is we have to find out, and net work is 30 kilowatt. So this gives me Q out as 70 kilowatt. So next is we have to find out calculate the amount of exergy destroyed and exergy rejected to the environment. So exergy destroyed is nothing but Q out your sink temperature. So assuming it is rejected to the ambient, so T naught is equals to TL. So exergy Q out is 0, because if you have a heat source at ambient temperature, you cannot generate any work. So the exergy is defined that the maximum reversible work which you can uh, obtain from the given uh, condition to the dead state, the ambient condition. So Ex Q out will be 0, Ex Q in is Q in into 1 minus T naught by TH, and W net plus exergy destroyed. So T naught is 298, 25 degrees Celsius, so 25 plus 273, and TH is 1000 Kelvin. So substituting as 1 minus 298 by 1000 into 100 Kelvin is the exergy because of the heat added equals 30 kilowatt net work plus exergy destroyed. So exergy destroyed is close to 40.2 kilowatt. So what this actually says is you are generating only 30 kilowatt of work, but you could have generated a maximum of 70.2 kilowatt. So if you are running a Carnot cycle, so your efficiency of a Carnot cycle is 1 minus 298 divided by 1000, which will be 0.702. So and you are supplying a heat of 100 kilowatt. So your if you are running an ideal Carnot cycle between this source and sink temperature, you would be generating 70.2 kilowatts of work, but this cycle heat engine generates only 30 kilowatts. So the rest 40.2 kilowatts is lost because of it's not being a reversible process, or because of the temperature differences in other, which is causing it to be irreversible. So that is accounting, and it's destroying the exergy by 40.2 kilowatt. So next is we are asked to find out the the efficiency. So here the work efficiency is net W net by Q. So Q in is 100 kilowatt and you are generating 30. So 30 by 100 is 0.3. So your exergy efficiency is nothing but your work net W net divided by your exergy of the maximum work, or the exergy of the Q in. So that will come out to be 30 divided by 1 minus 298 by 1000 100 kilowatt, this is 42.7%. So this is 42.7%. So we'll see what this means. So if you run a Carnot efficiency, so TH is 1000 Kelvin and TL is 25 degrees Celsius. So a reversible efficiency is 1 minus TL by TH is the efficiency of Carnot, which is 70.2%. So if you see actual cycle efficiency is 30%, but the Carnot efficiency is 70.2%. So this says that the exergy is nothing but efficiency by efficiency of Carnot, or you can say W net divided by the W generated by the Carnot. So 30 by 70.2 is 42.7%. So this says that second law efficiency or exergy efficiency is how close my cycle is to the Carnot cycle, because the Carnot cycle is the topmost efficiency which you can achieve. You cannot achieve anything greater than Carnot efficiency. Carnot efficiency is the maximum efficiency which you can ever achieve for a given condition. So how close are we to the Carnot cycle? So that's what is given by this exergy efficiency. So moving on, Rankine cycle. The compression and the expansion are adiabatic. The changes of kinetic and potential energies are negligible. The dissipation is neglected. Steady state operation. And so these are the assumption what which the Rankine cycle is given. So we have adiabatic process, and we are assuming that kinetic and potential energies are negligible across this turbine and pump, and there is no dissipation, and it's operating at a steady state. So the maximum pressure is 40 bar. So that defines my 2-3, that process is an isobar, so that is occurring at 40 bar. My temperature at point 1 is 35 degrees Celsius, and temperature at point 2 is 35.14 degrees Celsius. So this is very small rise in temperature. So average specific volume of liquid water V is 0.001043 meter cube per kg. So that is a specific volume of water, and water mass flow is 7 kg per second. And we have also given the saturated states of water for the two pressure ratios. So corresponding saturated liquid and saturated vapor, and the temperature corresponding to it is given, saturated temperature. So my lower pressure at 1 and 4 is 0.05622 bar, which is at 35 degrees Celsius. And corresponding enthalpy is H1 dash is my saturated liquid and H double dash is my saturated vapor, and similarly S dash and S double dash is the saturated liquid entropy and vapor entropies, and again it's given for 40 bar. Now they are asking to calculate the thermodynamic states at point 2 and 4, calculate the work and heat transfer during each processes, calculate the efficiency of the cycle. So we'll see how to solve this. The first is S2 is equals to S1, the compression process. So their entropy is defined for S1 is 0.5049 from the table which is given. So for pump, dH is V delta P. So being liquid, it's incompressible, so your specific volume there will be not much change, so you can assume that to be constant. So your work done will be minus integral V dP, so we assume V is constant, so it will be minus V integral dP, or V into change in pressure. So that is the work done across the pump. So your specific volume is given, and maximum minimum pressures are known, 40 and 0.05622. So substituting that, we will find out the enthalpy change across pump is 4.017 kilojoule per kg. So from this you can find out the enthalpy at exit. So H2 is H1 plus dH, which will come out to be 150.577 kilojoule per kg. H1 is nothing but saturated liquid enthalpy, which is 146.56. And similarly, you can find the vapor fraction at the turbine exit using the entropy at the turbine inlet, which is saturated vapor. So entropy at state 3 is 6.0685, and using the liquid and vapor enthalpies, saturated entropies at the lower pressure, you can estimate the vapor fraction at state 4, which will come out to be 0.709. So using this, we can find out the enthalpy at the exit of the turbine, so which is H4, which equals H dash plus H double dash minus H dash into X4. So this comes out to be 1861.02 kilojoule per kg. So now second question is, we have found out points 2 and 4. Now we have to find out the work and heat interaction which is happening during each of the processes. So we'll go each process one by one. So process 1, 2 is a compression process. So there it's the pump work, so M into delta H. So delta H we have already calculated, is 4.017 into mass flow rate is given as 7 kg per second. So it will come out to be 281.8.1 kilowatt, because we are assuming it to be in reversible adiabatic process. So your Q heat interaction will be 0, so Q is 0. Again, process 2, 3 is across a boiler, so where you heat the fluid. So there your work interaction is 0, so W is 0. Then heat which is added is M into H3 minus H2. So H3 is a saturated vapor at 40 bar, and H2 we have already calculated, which is 150.577. So substituting that will give me 18548.1 kilowatt. So that is the amount of heat which is supplied. And process 3-4 is turbine work. So turbine work is M is H3 minus H4. So it will come out to be 657.5 kilowatt. And because it's in reversible adiabatic process, your heat is again 0. So if you see, your turbine capacity is 6.5 gigawatts and pump is just 28.1 kilowatts. So that's a huge difference in the size of the pump and turbine. But if you saw in the previous Carnot cycle example, it was pretty close. So your compressor size is also larger. So process 4-1 work is again it's in condenser process, condensing process. So you are rejecting heat. So work is 0 and Q out is nothing but m dot into H4 minus H1. So it will come out to be 12001.2 kilowatt or 12 gigawatts. So next is to find out the efficiency. So efficiency is nothing but the net work divided by heat added. Net work is turbine work minus the pump work. So substituting the values, we will find out that the efficiency is close to 35.3%. So next we will move to see some problem zone and Rankine cycle again. We will see. So we have a steam power plant working on idle Rankine cycle. As the boiler outlet pressure of 1000 kilopascal and condenser pressure of 100 kilopascal. Find one turbine work output, second pump work, third heat input, fourth cycle efficiency, fifth steam rate, and sixth is moisture at the end of the turbine process. So these are the outputs which you need to find out. And what is given is your two operating pressures, 1000 kilopascal and your condenser pressure of 100 kilopascal. So this is how the cycle looks. So 1 to 2s is your ideal isentropic expansion, and 2s3 your condensation, and 3 to 4s your isentropic compression or pumping of fluid, and 4s to 1 is your heat addition. So here we know 1 is your saturated vapor and the state 3 is your saturated liquid. So we know two states, and the process being isentropic, we can estimate state 4s and 2s. So the first one is uh, from this state 1, H1 is your saturated vapor enthalpy. So for 1 megapascal or 1000 kilopascal is 2778.1 kilojoule per kg. So this value you can get it from the stream table. And similarly your entropy at state 1 is 6.5864 kilojoule per kg Kelvin. So similarly for pressure at lower pressure 100 kilopascal, your saturated liquid values, so H3 is saturated liquid enthalpy, which is 417.16 kilojoule per kg, and your entropy is 1.3025 kilojoule per kg Kelvin. And also we will require to estimate the enthalpy at state 2s, we need to find out the liquid and vapor enthalpies, or we can need to find out the latent heat HFG, which is 2258.0 kilojoule per kg. So S1 is equal to S2s because it's an isentropic process. So it will be 6.5864 kilojoule per kg Kelvin, and SFG2 SFG2s is 6.0588 kilojoule per kg Kelvin. So this SFG2 is difference between the saturated vapor and saturated liquid entropies. So from this we can find out the entropy vapor fraction using the entropy values. So substituting that, S2s is S3 plus X2s into SFG2. So substituting values, we will find out your vapor fraction at state 2 is 0.8721. So using this we can now estimate the enthalpy at state 2 or the turbine exit, which will come out to be HF plus X2 into HFG, which is 2386.36 kilojoule per kg. So next is for state 3. So state 3 is the working fluid is assuming saturated liquid. So we can find out the from steam table the specific volume. So specific volume is 0.001 meter cube per kg. So at state 3, so your pump work is nothing but WP is a difference in enthalpy into mass flow rate. So specific or you can write your work done is integral VdP or V3 into P4 minus P3. So as I told, because your it's incompressible, your specific volume will remain same, and I assume it to be constant. So this is what you get. So your work done, pump work is your specific volume into change in pressure. So 0.001 into 1000 minus 100, so will come out to be 0.9 kilojoule per kg. So from this you can also find out the turbine work. So turbine work is nothing but H1 minus H2s, so will come out to be, substituting the values, so get 391.74 kilojoule per kg. So now we can estimate the net work which is generated in the cycle, which is WT minus WP, which comes out to be 391.74 minus 0.9, which gives me 390.84 kilojoule per kg. So pump work will be nothing but H4s minus H3, so equals to 0.9, which we have estimated. So from this we can estimate the enthalpy at the exit of the pump. So H3 plus 0.9, so H3 is the saturated liquid enthalpy. So substituting the values, we will get enthalpy at exit of pump as 418.1 kilojoule per kg. So now the heat input Q1 is H1 minus H4s, so this comes out to be 2778.1 minus 418.1, so this equals 2360 kilojoule per kg Kelvin. So that is the amount of heat which is added. So now we have found out the heat input and the works. So now we can estimate the cycle efficiency. So cycle efficiency is nothing but W net by Q1. So W net is 390.84, which we have calculated, the turbine work minus the pump work, divided by the work heat input, which is 2360. So your cycle efficiency is 300.84 divided by 2360 gives me 0.1656 or 16.56%. So that is my cycle efficiency. So now the steam rate or specific steam consumption is 3600. It's in kg per kilowatt hour. So that nothing but your amount of steam required for generating 1 kilowatt of work. So to convert it to kilowatt hour, we multiply by 3600, the numerator and denominator. So 3600 divided by W net. So this gives me 3600 into 390.84, which is the specific work. So this gives me 9.21 kg or kg per kilowatt hour. So that is the specific steam consumption. And then moisture at the end of the turbine process. So moisture is nothing but your 1 minus vapor fraction. So 1 minus 0.8721 is 0.1279, so 12.79%. So it is 87.21% vapor, or you can say 12.79% of liquid is present at the turbine exit. So now the next problem is it's a combined problem with the previous one. So in the above example, if the pump work is considered negligible, calculate the cycle efficiency and steam flow rate. So we know how to find out the cycle efficiency and steam flow rate. So there we used the pump work. So here we are considering it negligible. So we'll see how much that is affecting. And then the additional is, if the turbine has an efficiency of 75%, calculate the efficiency, moisture content and steam flow rate. So assume pump efficiency of 0.75 or 75%. So now we are moving away from an ideal process to an practical. So the turbine it's not anymore a reversible process, but each turbine and pump has a efficiency. So how that is affecting? So we will see. So from previous problem, so we have calculated the turbine work is 391.74 kilojoule per kg. Now they are saying that my pump work is 0. So my net work output is nothing but the total work generated in the turbine. So W net is WT equals 391.74 kilojoule per kg. My heat input is Q1 is H1 minus H3, because H3 minus H4 is become 0 because my pump work is 0. So my H4 is equals to H3. It's more like an isenthalp, but you can also take the heat addition to be same, so that also can be done. Here it will give me 2360.94 kilojoule per kg. Previously it was 2360. So if you see, it's a very small marginal change because your pump work is 0.9. So it's a very small marginal change, so it will not make much difference. So still heat input is 2360.94 kilojoule per kg. So now the efficiency of cycle is again net work divided by the heat added, which is 391.74 divided by 2360.94. so this comes out to be 16.6%. so if you see in the previous problem it was 16.56. so here too, because we see the turbine work is 391.74, so we have 1 kg per second, so it will be 391.7 kilowatt. In the turbine work it is just 0.9 kilowatt, so it's a very small work, so it's not affecting much. You can straight away neglect it. So you have previous cycle efficiency of 16.56%, now you have the cycle efficiency of 16.6%. it's a very minute change. Now to find out the steam flow rate, it's again 3600 divided by the net work. So net work is the turbine work, so 3600 divided by 391.74, so this gives 9.19 kilojoule per kilowatt hour. So here it's 9.11, so here it was 9.21, so a slight reduction. So if you see there is almost no variation in efficiency and steam flow rate, indicates that WP is negligible. So that's no need to find separately, so they can straight away neglect the pump work. So next is assuming that your process is not reversible adiabatic. So we have some turbine efficiency and pump efficiency. So the turbine work is, if we go to the previous problem, it's H1 minus H2S for the ideal case. So now it is H1 minus H2, so that will have, it's not anymore isentropic, so you have some entropy which is generated, so there will be entropy increase from 1 to 2, and similarly for pump, so there will be entropy increase, so it will be not 3 to 4s but 3 to 4. If that's the case, so turbine work is H1 minus H2, so this can be found out using the turbine efficiency. So the turbine efficiency is defined as the actual work output divided by the ideal reversible isentropic process work output. So that is defined as the turbine efficiency. So from there we can find out the actual work output, H1 minus H2 is equals to your turbine efficiency into your reversible adiabatic process enthalpy change, H1 minus H2S. So from this your turbine work is 0.75, because 75% is the efficiency of the turbine, into your change, enthalpy change is 391.74, so this comes out to be 293.8 kilojoule per kg. So the input work to pump is WP by efficiency of pump, which comes out to be 0.9 by 0.75. so if you see the pump work now is 1.2 kilojoule per kg. So here turbine is the actual by the reversible the ideal, and for pump or compressor it's the reverse of that, so it's the ideal by actual. So because ideally compressor will take less work, but because of entropy generation, the practical is you will put more work, so that's what. So here again the pump efficiency is 0.75, so the pump work is defined by the ideal pump work divided by the efficiency of the pump, so 0.9 divided by 0.75 gives me 1.2 kilojoule per kg. So if we see, comparing to the previous problem, the turbine generated 391.74 kilowatts of work, but now it has reduced to 293.8 kilojoule per kg, and similarly the pump work has increased from 0.9 to 1.2 kilojoule per kg, taking into account of the turbine and pump efficiency of 75%. Now the net work output is equals to WT minus WP, which comes out to be 293.8 minus 1.2 is the net work, is the turbine minus pump work out. So this comes out to be 292.6 kilojoule per kg, and from this we can find out the enthalpy of the pump output to estimate the heat which is added. So H4 is H3 plus the pump work, so H3 is 417.16, the saturated liquid enthalpy, plus pump work is 1.2, so this comes out to be 418.36 kilojoule per kg. So now we know the enthalpy of the boiler in, so and the exit is the saturated vapor, so that enthalpy is known. So Q1 is H1 minus H4, which is 2778.1 minus 418.36. So this comes out to be heat addition is 2359.74 kilojoule per kg. So if you see here, the heat addition is reduced slightly compared to the previous one. So previously you supplied 2360.04 kilojoule kg. So here it is 2359.74. This is because the additional work which you are putting to the pump, that is increasing the enthalpy of the water at the exit of the pump. So it's the other way of increasing. So the heat requirement has slightly dropped, so very minute drop, and then we have found out the network and efficiency. So you can find out the cycle efficiency. Cycle efficiency is nothing but your network divided by heat input. So network is 292.6 divided by your heat input as 2359.74. So this comes out to be 0.124 or 12.4%. So you see previously it was 16.6%, so it has dropped by 4.2%. So taking into account of 75% turbine and compressor pump efficiency, so 25% drop in efficiency has dropped the total cycle efficiency by 4.2%. So next is the turbine. So H2 is, we can find out the enthalpy at exit of the turbine. H2 is H1 minus your turbine efficiency into H1 minus H2s. So, or you straight away know H1 minus H2, which is 293.8 kilojoule per kg, and we can find out H1. We know saturated vapor inlet enthalpy, H1 2778.1. So substituting that, H2 is H1 minus WT actual work, H1 minus actual work. So H1 is 2778.1 minus your actual work of 293.8. So that comes out to be the enthalpy at exit of turbine as 484.3 kilojoule per kg. So now we know enthalpy exit, and we also know the enthalpies corresponding to the pressure, exit pressure of the turbine. So using that we can find out, estimate now the vapor fraction. So H2 is 2484.3 and H3 is 417.46 and HFG2 is 2258. So substituting that, can find out your vapor fraction at exit as rearranging, it will come out to be 248.84.3 minus 417.16 divided by 2258. So this comes out to be 0.9155. So now if you see the moisture content which is there, which is 1 minus vapor fraction is the liquid fraction. So this is 0.0845 or 8.45%. So if you see, compare your drop in efficiency in the turbine from 1 to 0.75, that's a 25% drop in turbine has led to a lower moisture outlet. So in that way, having a not reversible turbine, so not having idle turbine is useful, because it's dropping the moisture content at the exit of the turbine. So say previously in ideal case your moisture content was 12.79, but it has dropped to 8.45%. So a drop close to 4% drop. So that is one good thing with having a lower efficiency turbine. But the next class we will see how what else can be done to improve the cycle efficiency, and also the moisture content, how to handle the moisture content. So that we will see in the next week class. So this so the inference which we are getting is the so we'll see the steam rate also first. The steam rate is 3600 divided by net work. So this comes out to be 12.3 kilojoule per kilowatt hour. So in ideally it was 9.19 kilojoule per kilowatt hour. Now it is 12.3. So what is happening now? Having a less efficiency turbine is less efficiency turbine and pump is creating more steam requirement rate or mass flow rate to produce the same amount of work. So you need more amount of steam, so that is increasing your capacity. So that's one thing. Next is your efficiency is dropping, and there's a small drop in your heat input. So they're very small because that is taken care by the pump. So that's one thing happening. But your net work which is generated has also gone down. So it is 292.6 in this case, and previously it was 391.74. So having a less turbine efficiency, less turbine and pump efficiency is reducing your cycle efficiency. You are reducing your net work which is getting. Your heat input is slightly reduced. Your then your steam requirement is has increased, and then the only good thing which we saw is your exit moisture content has also reduced. So these are all happening because of a less efficient turbine. So that's all what I have prepared for today. So I finished the problems pertaining to Carnot cycle and the Rankine cycle. So next week we will see how to improve the Rankine cycle or the other types of Rankine cycle. So having increasing the condenser pressure or dropping the reducing condenser pressure or increasing the superheat or increasing your boiler pressure. So what that does to a cycle, or doing a multiple reheat and between the expansion. So we have multiple turbines. So what happens to that? So basically how to increase the cycle efficiency of a Rankine cycle. So that's one thing which we'll be covering in next week, and also a regenerator cycle. So that will also be covered. So today was just basic of the Carnot and Rankine cycle. So that's it for today. Thank you. So we'll meet next week. Thank you.